Right, welcome to Unreal Fest, I guess, for everyone here. I'm John.
I'm Arcadius.
We make games at Aardman, which, yeah, surprise, surprise, we actually make games. And we're going to talk to you today about indoor environment creation in PCG, Geometry Script, and a few other tools. You're going to click for me.
Yes.
So Ark and I first worked together at another studio. We built a fairly comprehensive procedural pipeline to build sort of huge outdoor environments. And so in Houdini and UE4, and it was quite natural for us to pick up this project together to work on more sort of PCG stuff and tooling. We are not a tools team. We're quite a small studio, so this is really like a few sprints work between us. But it was a lot of fun, and yeah. So Aardman is hopefully some of you know Aardman. It is a historic Bristol-based in the UK animation studio, well known for Shaun the Sheep, Chicken Run, Wallace and Gromit, that sort of thing. And yeah, as I mentioned, we have a games team now, which we founded a few years back, and we also have sort of an interactive XR team. Our ambitions as a studio are to sort of bring some of I think our IP is very cultural sort of touchstones, and we're trying to sort of modernize some of the IP for new audiences and build new IP. The studio previously built 1111 Memories Retold a few years ago, which is sort of like quite an indie style title, and we restructured the studio for new projects, and we started this project in 2022 with Netflix. Scaled up the team to sort of manage that. And that sort of leads into this. Our current project is isometric stealth-like, isometric-like stealth action puzzler. Follows straight on from Aardman's recent film, Chicken Run: Dawn of the Nugget, which hopefully some of you have seen. It is mobile first, PC console coming later, but it's been designed from the ground up, well, to manage both, if you believe that's possible. That's a different debate.
Yep.
It is. We started on 5.1, so without PCG, and currently on 5.3, which we are upgrading soon. But we have got a major milestone at the moment, so we're not. That's on hold. The project heavily uses the Game Playability System, many other UE5 frameworks, so there would be like lots to talk about. But on this talk, we're going to focus on actually building tools to build our indoor environments. And this is interesting. Ark will talk about it in a sec, because a lot of the sort of ideal example situations of PCG are not that sort of environment. We have short development cycles on the for this project. Short development cycle. We did not understand gameplay when we started building tools, which obviously is difficult. And maybe do we understand gameplay yet?
I mean,
so.
yeah, the game just was not fun at the beginning.
But yeah, we didn't understand gameplay, so we wanted to build tools that were really flexible, that we could iterate really fast on, and we would kill our darlings, so to speak, so we could just throw away as much content as we wanted and iterate quickly. So we got a little short. This is really early footage, but. Cool, thanks. Thanks a lot. So obviously that says PC and console. Pretend that doesn't say that for this. We're not video editors, so that wasn't possible.
So we are not trying to suggest any specific algorithm. Say that right? Yeah.
Let's practice this so many times.
Or approaches. This is more of a quick review of how we've rapidly built tools for our team with these frameworks. So we have PCG. It is almost an exponential learning curve. A lot of depth, highly flexible, scriptable procedural content framework. I actually had to read that. It is data-driven and getting more so. Then we have Geometry Script. It is a geometric processing framework, fast and extensible implementation for many general mesh operations and manipulation. So if any of you used modeling mode before, it's something similar. I mean,
Yeah.
it's basically automated version of that.
It's a pretty good way to find out what features you can do.
Yeah, and it's really good for baking. Last thing we're going to talk about are scriptable tools. So it's like a simple tooling to build quick editor mode tools, and basically encapsulated the life cycle of our tools. So it was just very easy user interface for our designers and artists to just have everything in one place to play around. So we have.
So it's just saying artists and designers just play around. Does that make sense?
Yeah. Nice. So we have a couple of crowd questions. Any of you used PCG already? Okay. Oh wow, that's actually quite a lot. Any of you used the Geometry Script? That's a bit less, but yeah, still good. And any of you tried scriptable tools?
Okay, a couple of people.
At least we have some people.
Yeah,
that's cool.
good.
Yeah, that's good. So obviously, there are many different ways to build tools in Unreal Engine 5. Our requirements were that we speed up level building, encourage iteration, and art and design. They really wanted to have production-ready assets during whiteboxing, and we know how all that goes. But actually, these tools, PCG Geometry Script and scriptable editor tools, they seem to actually fit the bill, because it was very nice to actually upgrade stuff on the fly, and people would see actually this whiteboxing using those production-ready assets. So all of these fit the bill. What we didn't want to use were third-party stuff.
It's also for mobile performance as well.
Yeah, for mobile performance as well. Yeah, they actually they are really good for that. We didn't want to use third-party stuff because it was like Houdini, because it's just hard to maintain. And then if you go into C++ or Blueprints to build from scratch, it's just a lot of boilerplate. In summary, it was just really hard. It is really hard to convince people to try new tools. So when PCG was introduced for the first time, there was this like 1 hour presentation, 1 hour video by Epic, and there was like this 5-second clip of this building, and we were like, yeah, we want this, although it was just 5 seconds.
It was a nice validation, actually. We talked about using it, but we thought, would this map well to what we were trying to do, or were we just trying to fit a round peg into a square hole? And this validates it a little bit before we dug into it.
Yeah, I mean, and this is as well fun for us because we both work on procedural gen together, and John's academic background is in these areas as well. So our whole approach to building rooms is based around splines. Our actor blueprints, they contain its own spline and PCG component, in which the PCG component has biomes, different styles for each side, some niche features like, let's say, mirroring, some custom clutter on walls and bricks to break tiling, and we will go as well through custom spline work we did. Lastly, passages, because although we make rooms, we want to connect them somehow. And keep in mind, as already John mentioned, we didn't upgrade to 5.4 yet, so all of this you see is on 5.3. Here we are going to give you an overview of our room builder tooling. What is really important is that we are using data tables. As we were expanding the PCG graph, we didn't want artists to mangle too much, so we decided initially to have a data table which stores all the biomes and styles, and we actually really did like it. So for artists to just jump in, fill a style, add extra details to what they wanted to use, it was just amazing. And then we have a blueprint that covers corners, curved meshes using Geometry Script, which we'll get back to as well, and our PCG graph component. And although this looks maybe too simple, but I will actually show you how it looks in Editor. So, so this is our wall PCG graph. And what we do, because our blueprint actor has one spline, so we get that spline, we use our custom spline sampler, which John will get back to you later, and then we just filter out which segments of the spline are linear or curved. The reason is we just want to process the linear ones with PCG and the curved ones with geometry script. After that, we do a little bit of filtering. So we either put our passages or some custom meshes, even some hero assets, if I'm correct. Then after this, once we finish, so what we are left with are just where the points for the walls are. And
so yeah, you've specifically filtered out passages as well by this.
Yeah, passages. Yes, I did say that. Yes. So this is actually the main core logic of this blueprint, where we take our points, we give them an attribute of which mesh it should use, which material it should use, and then in the mesh spawner, we check these attributes, and it will just use a template to just spawn them. But the reason why we have it twice, it's because we get the same points, but we wanted to build on both sides different styles to have control over that. So as we separate this out, we just make a copy of these points and we just rotate them by 180 degrees. That's literally it. From this point, we started adding more like custom features. So in this case, we have mirroring. And what we do in the data table, we have an attribute to say, oh, do we want to mirror this specific style? And what we will, if we say yes, what we decided to do is we were just literally scratching the surface of PCG blueprint elements. So they felt very overwhelming and complex, but in all honesty, once you understand that there is a function called point loop body, which basically loops over each point, what we discovered is that if you break the in point variable, you can get something called metadata entry. And what this is actually the index you see in PCG of every point. So what we did, we took a modular, so we just filter every second, and we have a select node to just say, oh, either we don't flip it or flip it, put it back to the PCG point, and just return it. After this, we have a couple as well extra just added features that just requested, really niche. So for the input, for our crown logic, we take our wall points and whatever we filtered out previously for passages and custom meshes, and we first check with our data table, does this specific style use crowns? Then we add the mesh, and then because we didn't want this specific thing to be double-sided, we actually choose from which style we want the crowns to be spawned. After that, we just transform them a little bit higher on top of the walls. And again, same logic, use the string to just spawn the mesh. Next section is actually spawning clutter on walls. So again, we just check, do we want it for this side or the other side? We then give them some custom offsets if they require. Then if they were mirrored, we actually unmirror them. And after this, we have this now spacing logic. So you can either go with select points node, which is built in, which will randomly choose a selection of points. You can as well give your attributes from your datasheet to be referenced, so you can control it. Or you can do another custom blueprint. So this one is as well doing the same thing. We are getting our points, we are getting our index, and instead of filtering every second, like for mirroring, we are making a new attribute, which you can easily build in. And then we are just selecting, is this true or not, and what this does. If it's true, the point will be kept. If it's false, the point will be discarded. Yeah, discarded. So after that as well, our data table can control for certain style how many walls we want. And the next section is our specific clutter. So in this case, artists really wanted to just have clutters on specific style. So we are checking
Wall clutter.
small wall clutter, yes. So our logic basically checks if the point is supposed to use this specific mesh. If it's using this specific mesh, spawn this type of clutter. If it's this specific mesh, spawn this type of clutter, and so on. Last and least, we have bricks.
That's not the saying.
I know. So we have bricks, and for bricks, there is a node called import data table, which is different to the new load data table. But what this does, you can actually import a specific set of points. So we made a data table with hand-placed points of like typical brickwork.
You say we, I definitely did not do that.
Yeah, you did help. And then what we actually do, we take our wall points and we copy those for each wall point. After that, we again do a random selection, could be defined by data table, could be defined even per blueprint, you can overwrite this. And then we do some scaling. After that, there is this kind of interesting system for static mesh spawners, where you can actually make your selector type a PCG mesh select weighted by category. And what this does, that if you have a certain category that it expects, it will look through the array and see which meshes should be spawned for this type of array. So in our case, we have a mana garden style, and then it will just spawn these 4 meshes. If we would have a different style, it would look for a different index. Yeah, and that's it for this wall. So here we have examples of what we did. So we have the two-sided style, the first image. You can see, so we can independently control which style we want on the wall. After that, we have our custom overrides for any kind of custom mesh we want. It just checks the wall and checks what should be spawned there instead. Next is mirroring, and this is a specific style where we just did like one side of the wall and the next one is just flipped, so it looks nicer. After that is clutter. As well, could be manually overridden if an artist is unhappy. They usually were unhappy with how it looked. After that is crowns. So as well, again, we just have these extra meshes on top to add a little bit of style. And last and least are bricks. So as you can see, so this is like the initial pattern, and then we filter out and we can scale them. And yeah, the bricks tiling, which is pretty cool in my opinion.
I'll briefly talk about the spline sampler that Ark mentioned. So what Ark said at the beginning is our room building tool is essentially based around splines, but really it's actually based around the discretization of splines, right? So we are generating PCG samples along the spline, and we are then tessellating meshes along that spline to make it look like a contiguous sort of room or wall. There weren't really any samplers that fit the bill for us easily out of the box, so we built our own. This is actually very simple. You extend UPCG settings, which is a class in the PCG framework and plugin, and you can set up custom params. That's quite straightforward. And essentially, we are overriding the F subdivision step sampler, which is which is a class which extends F step sampler. Within the step function, that's where most of our logic is for doing this. So essentially, what the normal input for subdivision sampler is to take like n points and sample that uniformly according to some rules along the spline. But we wanted to do it according to a mesh, so whatever mesh we would feed into it or set of meshes, we would get an output. So basically, instead of computing like the subdivisions, instead of passing the subdivisions per segment as a parameter, we compute that inside this function. And then we just compute the out transform, including like the distance along the spline and the scale, based on the mesh that we input. and then fixing up indexing, which is a little bit different to the normal subdivision sampler. So that gives us a really simple way to just automatically tessellate any spline with the mesh that we put in. What we also can do there, we have a slightly more accurate curvature computation. We can compute some other stuff in the step sampler as well, which is quite useful. These are all written as attributes, as Ark mentioned. PCG is kind of like similar to a pipeline where you're reading and writing from attributes all the way through that pipeline to allow you to do filtering and different stuff along that sort of PCG pipeline. So having our custom sampler means we can just we can compute new attributes alongside that. And you can see the GIF here. By the way, this talk is basically just GIFs. So if you like GIFs, then that's great, as you've already noticed. If you don't, then this is probably not the talk for you. Yeah. Cool.
Oh, okay. So we need the passages for our rooms because we just need to connect them somehow. So these were our doors, double doors, vents, and even artists said, we add windows to it so we can manually control where they are. We were like, okay. The simple solution was just replace the PCG wall sample with a passage. However, this restricted design because they just couldn't, tweak a little bit the doors to the left, to the right.
Also, it's super fiddly.
Yeah, it is super fiddly. So instead, we just said, just place the passage where you want. And what we did is we insert a spline control point either side of the passage. And because of how our spline sample works, it will auto-compensate for the meshes around it, as you can see in the second GIF.
Like right at the end of the second GIF, which you have to wait for the entire time. That was really well done,
That's it. Yeah.
There we go. So that's the different approaches, like that GIF, just to let you know, that's not the approach of fitting a passage. Like you just click and it just fits a passage. So that's the work in progress. We thought we'd briefly talk about the fact we use custom splines, which I'm sure most projects do. So we built our custom spline component, and that obviously has spline metadata and spline metadata details. The custom spline we use for various different things throughout the project. In this case, we just embed, most of the use cases for this, we do some interpolation, but most of it is embedding metadata in our spline control points. As probably a lot of you know, there's a lot of boilerplate to implement this in Unreal, which is a bit fiddly, but it's quite straightforward. This allows us to have custom corners per control point. So these might be like turrets, or they might just be like tiny little things, like in this GIF here. And this is great because it allows, sort of breaks up, the thing, and they can designers can control whether this appears on every corner or not, and sort of manually control the offset. It's also sided, so as you move the wall around, it generates the offset on the right side of the wall. We also have, again, Spline Component Visualizer, which we use for various functions throughout the project. This allows, as I'm sure, again, everyone knows, this allows us to decouple functionality from the spline component, or add easily functionality to the spline component. An example of this is because we've got these large rooms and large walls, and obviously people don't use the tools as we intended. So instead of building small little cute rooms and stuff, and then and having that, they build enormous walls like hundreds and hundreds of meters long, and then complain that the pivot's too far away, etc., etc. So we just have a tool in the spline component visualizer that allows us to split a spline, split a wall, and it just generates two PCG graphs, regenerates themselves, inserts control points, and changes the pivots and stuff, and just as a right-click menu. So that's super good for separation of functionality there. So quickly, how we handle curved walls. So Ark mentioned curved walls in the PCG graph. Our original idea to solve this seemed like a super cool idea.
No, it was a bad idea.
Yeah, it was. We were convinced that this was the right idea, as many of us are on projects. And the idea, I think it sounds sensible, but the idea was basically to hand it all in PCG and materials. So we would just treat a wall segment as a curved wall segment. We would sample it in the PCG graph as before, and but then in material, curve that mesh locally, that instance locally. Did you mention it? So all these are obviously instance static meshes, and we would curve the mesh locally and in the material to bend it to the spline, essentially, using custom primitive data which you can send in PCG. So The problem with that was that we would, well, it was quite complicated to do in the material. It was quite complicated to get it to follow a spline locally. You had to send quite a lot of data. Math was fairly messy. And so also, this has actually turned out to be quite a lot of performance overhead to do that much vertex transformation on the GPU every frame. So our interim solution was to filter out the curve points. So we look at the attribute sheet, as Ark mentioned, filter out any points that have negative or positive curvature, and throw them away pretty much, and then insert a spline mesh, and that would follow it. We could set up the material sort of basically, and that looks fine, sort of. Actually, it doesn't look fine because you can't flip elements. We can't have custom materials. It's problematic, and if the curvature of the mesh is high, we get lots of errors because the spline mesh won't handle that properly. So our solution was to build this in geometry script. So we kind of use the same approach with the spline mesh. So we filter out the points, throw that away, and then we feed it. So Arc then parameterizes this geometry script class we have, and that basically handles that'll map this. So that'll still tile this instance mesh as we want across the curve. It'll handle backwards and forwards, and it will curve it properly to the spline. But also we can do things like subdivision and decimation and stuff to make it curve really well. It's a single draw core, sufficient. We have the dynamic mesh actor, which I'll talk about in a second, which allows like a non-destructive workflow with the PCG graph. So it sort of handled everything really nicely. And I'll just dig into that a little bit now. So this is an example here of this is a PCG wall graph in the GIF, and just modifying the curvature of the spline. And this is generating geometry script curved wall on the fly, which is baked down to a static mesh on the fly as well, but is fully reversible. A bit like, I don't know if anyone's played around with Lyra, they do something called cold storage, where they sort of maintain the references for the dynamic mesh and the static mesh, so you can flip back and forwards when you're moving windows around. So geometry script is based on dynamic meshes, which, as you can tell, you can sort of guess what the difference is there with a static mesh. It is based, like in Blueprint, you will extend a generated dynamic mesh actor, and like normally, instead of then tying stuff into a construction script, you'd use the on-rebuild generated mesh function, which just sort of performantly handles that rebuild at runtime in the editor. There's some other functions in this class to handle copying back and forth between static mesh actors, showing progress in editor if it's a large rebuild. But broadly speaking, it's just this is the sort of environment you'll be working in. And I'm just going to briefly talk. Okay, so the core approach to this is that we sample the spline, the curved segment of the spline, spawn static meshes, and then deform them locally to match the spline. Then we sort of bake this down and release all our assets. And I think, here we go. So I'm just going to show you this blueprint as well, just very quickly. So essentially, this is our function, the rebuild generated meshes. We do a bunch of allocation of our dynamic meshes here. And then, first of all, we handle the front side of the spline to handle like our inside meshes or outside meshes, depending. So as you can see, the component, the actor is quite simple. We have a front spline and back spline. Then most of the functionality is in this build and aggregate mesh function here. Inside this, we essentially copy from the static mesh into our dynamic mesh object. Then we apply uniform tessellation here. So this allows us to obviously really increase the density of the mesh, which allows us to then deform the mesh accurately and then simplify it afterwards. These are just standard geometry script functions. So then this is a custom function here. So the mesh sample spline to transforms. So there are some spline sampling functions here, but again, we wrote our own for this. This allows us to sample the spline according to the mesh size in whatever axis we specify. And from that, we get out these frame times along the spline and a uniform scale for the spline as well. This also allows us to adjust for where the pivot is on the input mesh, depending on how the artist has decided to build it. And essentially then we copy this template mesh, which we've subdivided once. So we only sort of subdivide once in every process. We copy this to our spawning mesh, which is what we're going to modify. This is a bit of a hack here, just to handle the mirroring Arc showed on the PCG graph, like where like inside castle walls are like flipped every other thing.
Hack, yes.
Yeah, and which is a hack in that as well. And this is where we, this is the interesting function here, where we deform the mesh to follow the spline. I'm not going to go into it here, it's a bit too much to go into, but essentially it's some fairly trivial linear algebra to follow the spline, to deform the mesh locally, scale it in X as well, which is, this is our axis for our wall pieces, and to deform it locally to follow the spline. Pretty much kind of similar to the function used in the spline mesh component. Then we append it to our aggregated target mesh, which is another dynamic mesh. We set up materials and UVing and recompute our normals here. We do this once afterwards, so we get smooth normals, obviously, across the curved segment. And then, so basically, we do that for the front side of the mesh. We then have a custom function to reverse the spline, do it for the back side of the mesh with a different source static mesh. Then we aggregate these two meshes. We apply some planar simplification. The reason why we use the planar simplification here, there's a few simplification methods, is this allows us to give an angle for control, which means we can sort of almost like enforce the quality of like how we're using the curvature. So it like allows us to like have a minimum quality there for that, which is useful. Then we release all our resources. We have this function here. We don't use it here. Like Arc actually calls this from the PCG actor, which also owns the graph. But this handles the baking to a static mesh, so auto-naming, adding to source control, et cetera, computing collision, stuff like that. So that's then called, and in the PCG graph actor, that manages the state, like cold storage back and forth between the dynamic meshes stored here and the static meshes output from this process. So that is a quick run through of what we're doing in the curved mesh stuff. And here is just a quick thing. This was a GIF, but it was so hard to follow, I couldn't describe it. So I actually converted it to images, which is a bit of a breath of fresh air. So you can see on the left, I'll go through this pretty quickly. On the left, we have like the normal mesh, if we don't do any subdivision and decimation afterwards. And you can see it's like, like it's an optimized mesh designed for sort of mobile. These are all instances, by the way. Well, no, they're not anymore because it's baked down. This is a normal wireframe. You can see subdivided, we have this very high poly count, but we match the curvature. You can see the errors on the leftmost curved wall. Like if we don't subdivide first, it looks rubbish. And then we can decimate afterwards. So these functions here are all part of Geometry Script, right? Like this is not our sort of novelty, but it's just really useful to be able to do this in Geometry Script really easily. And like it's much more efficient and useful to us than using the mesh spline. Spline mesh, sorry. Quick other algorithm we built. So we built something to like enable, like we have lots of non-sort of rectilinear rooms or like all sorts of odd shapes. We have curved rooms, and because you're looking top down, you can see the extent of all the floors. So we built this quick tool to allow you to generate floors in the level very quickly. This is a custom algorithm, so I won't go through it in much detail because it's less relevant to this talk, but it does use Geometry Script, so we thought it'd be interesting to mention. This sort of allows really quick automatic generation of floors. You basically click, it uses a geometric flood fill. It builds a data structure that allows fast neighborhood lookups, so you can do like more interesting stuff with that data. But essentially, we build a boundary for this, generate a poly from the boundary. Most of the complexity in this algorithm is handling edge cases. As you can imagine, with like really concave polys and stuff, it's pretty nasty, especially when we're like tracing out into the wall geometry to figure out where the floor is. But basically, this is not super clever. It just allows like artisan designers to quickly build floors for a level. So this is all built around Geometry Script as well, and we generate a dynamic mesh from this poly, which again we can use this sort of like it's almost a cold storage method to go back and forwards between the static mesh and our dynamic mesh, except actually in this case we throw the dynamic mesh away because for just more like to be a bit more optimal, if you sample the floor, as you can imagine, there is a grid, so like it's not completely deterministic, but if you sample the point at the same place, it's completely deterministic when we regenerate this floor. So that's all we store when we go back and forth between this. So you can easily like move a wall and regenerate this, and then it doesn't use the same footprint in your project. This obviously bakes all these static meshes to like automatically. You can see the sort of naming when you build this. It generates this and writes it to the project structure and etc. It does a uniform remesh on it. I think you can see it in the last thing. Actually, you can see when it builds this mesh, we do a remesh of it, which is pretty optimal for the project. You can see when I just drag this up.
Yeah, GIFs.
GIFs, more GIFs, have to wait. There we go. So it produces a fairly simple thing. We could probably make that more simple. But we also have this space delimiter thing. So using this neighborhood structure, we can detect gaps. So if like someone set a room up wrong, it gives them a giant instruction, like a massive red arrow to show them where they've screwed up the room, basically. We also generate a boundary spline from this. And the reason that's interesting is we use it for like room clutter and other things down the line. The reason why we don't just use, the reason why we don't have that boundary spline anyway is because, as we said, like we thought people would just build rooms, right? But actually, most of the time, they just add a little bit on. They build a wall, and then it creates a room, like implicitly from the connection to other rooms. So building this boundary spline is really useful for later clutter generation, which we're going to talk about now.
Yeah. Okay. So our room clutter is very artist-led, because they just wanted to place everything by hand. So we said, yeah, go for it. And as they were building, we've noticed that there were a lot of rooms where they were like stacking boxes on top and so on. And we were like, you can just use physics simulation for this. And I mean, they were happy with it, but then we've decided to actually go deeper into BCG. So at this point, I've discovered this three-dimensionality of attribute sheets. And what is really cool about this, you could create a data table where you have each of your mesh stored in a different row with some data. And then what you can do, you can load that data table into PCG and then use this amazing node called attribute partition. And what it will do, it will take all these, if you sample by the mesh, if you use the variable from the mesh, it will split this attribute sheet, each point, into individual attribute sheets, each one containing one point.
I can see this somehow blowing your mind, even talking about it.
I mean, it was really exciting. It really did blow my mind. But what is cool about this, you can actually then go into subgraphs, which are as well really, really useful. So there is a node called loop subgraphs. So what this does, this will actually loop independently per attribute sheet you feed to it. So in the GIF you see, we are actually having a room, we are filtering some logic, but then once we filter through all of the clutter, we put them all together so they are bunched up, overlapping. After that, we use a prune node to just make sure they don't overlap. We spawn them as static meshes, then we run simulation and just bake the output. And artists were quite happy with this.
Yeah, we kind of went rogue on this one because normally we're just following, reviewing whatever tools our artists and designers want and then talking to them about it. This one, we were like, I think this would be useful, and we wanted to try out some new stuff. So obviously, like our art director would probably look at what you generated here and cry. Yeah. But it's a good starting point. I think this is also on our previous procedural project that we worked on in our last company. Having a basis for artists and designers to start from is sometimes part of the goal. So like generating enough for them that it's not scary to start on this level is often like really useful, and I think that fills that.
Yeah, and you can easily build like rules for different rooms. So in our case, we could like build clutter for storage rooms, build for kitchen and stuff like that.
So now we're going to give a quick talk about scriptable tools, which interestingly was the least known about thing in this room, I think. It's very simple. It is a framework for building like really trivial custom editor modes, basically. It allows you to, it's like as a programmer, it's a fully like, you can separate concerns and sort of encapsulate stuff differently. So it's almost, you can very trivially follow like some sort of MVC pattern with your tooling. So you can build your tool completely separately and then build your scriptable tool and just wrap functionality with it. And which makes it really useful to build. It's modal, so it has a pretty well managed lifecycle, though I will go into that in a bit. It's amazing for building quick stuff. You can see like we built a few tools here as an example to show you what's going on. There is the three main classes that you'll end up using: a scriptable single-click tool, a scriptable click drag tool, and I have to read this one out: editor, scriptable interface tool, interactive tool, property set.
That's a really long name.
Yeah, I think this is proof that Epic don't review class names in their process. So if anyone was ever wondering, I think we've proven that. Feature-wise, you get lifecycle support, which you have to put some effort into. Click, drag, hover, It's largely event-driven, so it's really straightforward to use. You can add gizmos to anything you like, property watches. So if you change data, you can rebuild automatically. And you might be scratching your head, asking, like, wondering what I'm actually talking about here. But I'll show you the tool on the next slide. Messaging help on screen, rendering, simple HUD, serialization through your property set, etc. Actually, that property set thing you don't have to use, but it's quite another way to separate your data from your tool. So it's kind of good to use it, I think. So this is an example of using the tool. So you can see the interface here. So like you choose your tool on the left, a bit like if you've used modeling, well, if you've used any editor modes really, you choose your tool here and set it up. And you can see on the left, like I realize there's like 3 GIFs and there's a lot going on here. So if you try and follow what I'm talking about. So the left one is our wall builder, which you can see in the scriptable editor tool. So this is our wall builder tool, a room builder, sorry, wrapped with a scriptable editor tool. So you can see I've got gizmos on here by default, which is probably stupid. It makes it quite confusing to see what I'm doing. But you can just toggle this on and off. And when the GIF restarts, I'll sort of talk through it. So you can see I'm just sort of placing points here. Yeah, now I'm placing points here. I can modify them in real time with the gizmos. You see I sort of label the head and tail with the message text to make it clearer. And you can see also I've turned snapping on there. So this is handled through a modifier, through the control modifier. And that allows snapping to tiles, which is super useful. That's not part of scriptable tools, really, the snapping, but the modifiers are. Then that's a shift modifier to insert a point. You can, it's really flexible for what you're doing. You can also, we've done stuff so you can just like add to the head or the tail of the spline. It's like a super useful interface for drawing splines. Then we've got our passage tool here, where sort of Ark mentioned the complexity of the passages and how they're a little bit tricky to set up. So this tool just simplifies that. So you just choose the door you want, and you just click anywhere on the level. It just inserts it in a wall. So it's like takes 10 seconds to put doors in the entire level, which is like super useful. Then the floor tool, finally, you can see when the GIF restarts that I just click around, generate all these polys for these floors. Which this is obviously like the floors on this level are quite sort of rectilinear. In fact, they're quite rectangular, I'd say. So it's not a super good example, but it is dense and complicated, and there's loads of geometry and stuff. And then I just like generate all those, bake it down instantly, and then you can drag and drop like materials into the scene and completely build out all the floors in the scene super quickly. And again, that is like part of that utility is from how good scriptable tools are, just as a really quick tooling system. This is this is just our learnings from using scriptable tools, which I thought would be interesting to briefly talk through. So modifiers don't actually work super well out of the box. They work well in terms of like when you're setting up your blueprint scriptable function, which again is just sort of a bunch of events, like you have a startup event. It doesn't handle modifiers too well. So you'll get modifiers like Shift key, Control, Alt, which is what it supports out of the box. But they will only work on like your startup and your click like events. So if you're like having a mouse hovering, which is a lot of what probably a lot of the way you will use the tool, that won't update your modifiers. So this is just, I thought I'd just put this up here to give an example. So if you extend this tool and just override the setup function, then you can just bind events to like some of the other events happening. So you actually get real-time modifiers. Otherwise, if you're hovering, not clicking, and you press Shift or Control, you won't get these updates. So that's kind of useful. We added support for viewport grid snapping into all of our tools and throughout the project. So this is just this very simple function that grabs that from the viewport. So like, when the user's just changing the viewport, you can just grab that value. So whatever that value is will be used throughout our scriptable tools as well. And then as you can see in the blueprint thing there, we can just grab that value and snap to grid. State saving is a little bit nuanced. You kind of have to do things in a certain order to make sure that state saving works. So you can serialize data between sessions in your property set, but there's some nuance there, so that is a bit fiddly. Complex watches don't work. So you can drive property change events, basically, and they don't work for complex types. So you have to either roll your own. So assume if it's a basic type, you will get a watcher, like an event from that. If it's not a complex type, that probably won't work. Just bear that in mind. Clean up very carefully. So it is modal. It does handle its life cycle, but there's like a shutdown thing event which you will have to manage stuff from. It's very simple to, and obviously if you can get selected actor as well in a scriptable tool. So you can actually load an actor in. You can load your complex wall in and just edit it. So obviously if you're loading that in, you don't want to roll back to like no content. So you need to handle that rollback properly. Obviously, very simple to wrap stuff for. There are, not that we found anyway, there are no default delegates for when a PCG graph is rebuilt. So if you're wrapping PCG stuff with this tool, you need to write your own stuff, probably we can find it anyway, to handle when a graph is being regenerated. So that is like, obviously a process. You can't like by default hook into that.
So yeah, extra bits. We've built an editor widget to help us handle regeneration because it was like a little bit difficult to like updating the PCG, then regenerated it per map. One thing as well we did try to fix. There was a little small bug when you try to do Control-Z undo, it would leave like ghost meshes in PCG. So as well we tried to fix that. The other thing we've added were bushes. So as well, this was very niche for like one specific map. Somebody was asking to do like kind of maze out of foliage. So yeah, we just made this kind of guide splines you can use for PCG. And now as you've seen this maze, we will have to change because you know the solution.
He's been excited about telling that joke. I'm not sure why.
Yeah, last thing are tunnels, and as well, this is the same kind of idea with having straight lines handled by PCG and then curved by geometry script.
Cool. So just a couple of slides to wrap up on future work. Do you want to go first?
Yeah. So for PCG, we would like to have more of a global way of manage and regenerate and test the PCG graphs in the project. We wanted to do.
The reason for this, by the way, is like if you build your PCG graph and you generate some stuff on a level, and then you forget that level, don't work on it for like 3 months, and you've changed the graph a lot, like that won't be regenerated in that level. And also, like we don't know quite how to handle that. We don't just want to regenerate anything because that's a QA nightmare to then regenerate everything and not go and test it. So it's a bit nuanced to us how to handle that, I think.
Yeah. Another thing we really want to do is roof generation. So currently we could just use the flow builder, have a flat roof and just move it up. But we would like to actually try to do some kind of more complex stuff and as well, build different ones for different styles if it's possible.
Yeah, I think this is just out of scope of the project really, because if we're building roofs for like rectilinear buildings, then it's reasonably straightforward. And as soon as you add curvature, it becomes even more tricky. We just didn't have the time to work on this really. So that would be something we would like to do. Sampling patterns. So Art mentioned we have this data table with samples for brickwork. We'd like to use, there is actually a plugin called PCG Geometry Script Interop, which allows PCG to call some of the sampling functions in the Geometry Script library. We'd probably like to add to that to add some more like noise patterns and sort of industrial patterns to make wall clutter. We currently don't handle passages on curved walls. This is not because it doesn't work. Obviously, this would actually be quite straightforward, carving into the mesh with like a Boolean op or whatever in Geometry Script. We just haven't done it. We haven't had time. And Floor Builder, the artists want like ways to build to explicitly define like split room floors. That wasn't described very well. So if you have some giant room, they want to be able to draw a boundary and like split that into two things. So we'll probably do that. Also, not auto regeneration as such. That's a misnomer really. But be able to click a button to regenerate it based on what the room changes. Hierarchical fog of war is something I'm not going to go through because we don't have time. But there we go.
Yeah, the takeaways. So it is great to build tools around these amazing frameworks. If you want to go through consider your sampling strategies, how you want to sample the data. Consider using subgraphs. They are very, very powerful, and as well, use data tables and data assets. They really help you to do more versatile work.
That's got a lot more flexible in 5.4. Well, 5.3 and 4 utility of those. That wasn't available really when we started. Geometry Script is super flexible. Dynamic mesh is very useful. I think there's real utility in non-mobile projects for using dynamic meshes in release as well. I think someone told me the other day that you can use that with Lumen now. I think there's real utility there, but also all the tools to bake stuff down, it can be very efficient for mobile. And there's just having the flexibility to do a lot of these mesh operations in Editor is super useful. Scriptable tools, as you've seen, utility is incredible for something that's so easy to build. You can build these in like an hour or so and have a tool that is far more usable than the tool you had before. And yeah, like just to say, really, this has been continued development through the project. So when we like the original thing was pretty bare bones. You could sort of see, I think, the life cycle from Arc's PCG graph. As like right at the beginning, we were both looking at that to figure it out, and then Arc's been working on that over the year. And like I guess his knowledge of that has changed a lot, and also the tooling for that with 5.3 and 5.4 has changed a lot. But this is really just like us building these tools throughout the year, like just in our spare time, really, like moments here and there to try and build them out. But yeah. Anyway, thank you very much. And that's the end of our.
Thank you.